Pluto is a distant and clandestine, more modest planet that was once a part of our planetary system. However, recent disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a dazzling revelation. They suggested that this chilly world is on a potential collision course with Neptune. But how could this actually happen, and what might be the consequences of such a colossal event? Are we witnessing a fascinating cosmic anomaly, or is there something more to this looming catastrophe? Join us as we examine the possible outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading specialists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a possible collision between these two celestial bodies, which could pose a tremendous threat to Earth. Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it has not yet completed even one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is exceptionally elliptical, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees to the ecliptic plane. This inclination and eccentricity add layers of complexity to its orbital motion. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's. For approximately 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, challenging common expectations about their positions in the solar system. The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to understand its unique path. Unlike other planets whose orbits relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these peculiarities, is a testament to the complexities of celestial mechanics. The three-body problem in space, determining how three objects such as Pluto, Neptune, and the Sun move and interact gravitationally, is a fundamental challenge in astrophysics. This problem illustrates how Pluto's orbit, Neptune's orbit, and the Sun's gravity work together in a delicate and complex manner. Asynchronous libration. This ensures that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from converging. Orbital precession. This refers to the gradual shift in Pluto's orbit over time. It causes Pluto, when closest to Neptune, to be positioned far above or below Neptune's orbital plane, providing an additional layer of protection against collisions. The VZK oscillation, named after three researchers, this concept explains how gravitational interactions among Pluto, Neptune, and the Sun contribute to Pluto's long-term orbital stability. Despite appearing chaotic, Pluto's orbit follows predictable patterns over long periods. These factors collectively ensure that Pluto and Neptune remain in stable orbits without direct collisions. However, numerical simulations in the late 1980s revealed that Pluto's orbit is actually volatile over very long time scales. Minor changes in initial conditions can lead to significant variations in its path over thousands of years. Further studies have demonstrated how the giant planets Neptune, Jupiter, and Saturn influence Pluto's orbit. Neptune and Pluto share a 3:2 resonance, meaning that for every 3 orbits Neptune completes, Pluto completes 2. This resonance plays a crucial role in maintaining Pluto's stability. However, Neptune is not the only factor at play. Jupiter's immense gravitational influence also stabilizes Pluto's orbit, ensuring it does not stray too far into Neptune's domain. Saturn further contributes to this gravitational balance. Without these stabilizing mechanisms, the solar system would be far more chaotic, with bodies like Pluto potentially colliding with other planets or being ejected into interstellar space. Understanding Pluto's orbit is crucial in assessing the potential risk of a future impact. The case of Pluto exemplifies how even seemingly unstable orbits can achieve equilibrium through the interplay of gravitational forces and orbital mechanics. It underscores the importance of continuous observation and research to deepen our understanding of celestial dynamics. Pluto's orbit also illustrates the concept of orbital chaos, a phenomenon where small variations in an object's initial position or velocity can lead to vastly different long-term trajectories. Programmatic simulations have been invaluable in modeling these effects. Studies from the late 1980s showed that despite stabilizing factors such as asynchronous libration and orbital precession, Pluto's orbit can still exhibit erratic behavior if even minor deviations occur in its motion. Yet even with this unpredictability, Pluto's orbit remains stable over billions of years. This suggests that while short-term fluctuations exist, its long-term trajectory follows a pattern governed by celestial mechanics. Predicting celestial events, especially those involving complex orbits like Pluto's, remains a significant challenge. Numerical models provide insights into Pluto's future trajectory, but they are limited by the accuracy of initial conditions. Small uncertainties can lead to vastly different outcomes, making precise long-term predictions difficult. Neil deGrasse Tyson, a prominent astrophysicist and advocate for science communication, has contributed significantly to discussions about Pluto. Known for supporting Pluto's reclassification as a dwarf planet, Tyson emphasizes the evolving nature of our understanding of celestial mechanics. He views Pluto's orbit as an example of how much we still have to learn about space. However, despite his optimistic outlook, his concerns about Pluto's long-term orbital stability suggest that many mysteries remain. Could Pluto eventually crash into Neptune, or is this another misinterpretation of orbital mechanics? Only time and further research will provide the answer. For now, this debate fuels our curiosity about the intricate and unpredictable nature of our solar system. The possibility of a Pluto-Neptune impact challenges our conventional understanding of planetary stability, reminding us of the dynamic nature of the universe. While a collision remains unlikely due to the 3:2 orbital resonance and stabilizing gravitational forces, the theoretical implications of such an event are fascinating. Given Neptune's immense gravitational field and Pluto's icy composition, an impact would have dramatic consequences potentially visible across vast distances in the solar system. Ultimately, while Pluto's orbit may seem chaotic, its stability over long time scales is a testament to the incredible balance maintained by gravitational forces. As researchers continue to refine their models and gather more data, we will gain deeper insights into the intricate dance of celestial bodies that shape our cosmic environment. The potential for a Pluto-Neptune collision remains an open question that continues to intrigue astronomers and astrophysicists. While current gravitational models suggest stability, there is always the possibility that external factors such as gravitational perturbations from other celestial bodies or even passing interstellar objects could slightly alter Pluto's orbit over extremely long timescales. Beyond the gravitational interplay of Neptune, Jupiter, and Saturn, other factors in our galaxy could influence Pluto's trajectory. For example, interstellar objects. The recent discoveries of interstellar visitors like Oumuamua and Borisov suggest that rogue objects pass through our solar system more frequently than previously believed. A close encounter with such an object, depending on its mass and velocity, could impart enough gravitational influence to nudge Pluto's orbit slightly over thousands or millions of years. The galactic tide. The solar system orbits the Milky Way's center, moving through different regions of varying gravitational influence. Some studies suggest that this galactic tide could slightly perturb the orbits of distant bodies like Pluto and objects in the Kuiper Belt. The hypothetical Planet 9. Some researchers hypothesize that a yet undiscovered massive planet lurks in the outer reaches of our solar system, exerting gravitational effects on distant objects, including Pluto. If Planet 9 exists, it could subtly influence Pluto's long-term orbital evolution. If against all odds Pluto and Neptune were to collide, the consequences would be profound. Given their vastly different compositions, Pluto being an icy rocky dwarf planet and Neptune a gas giant, the nature of the impact would depend on several factors, including the collision velocity and angle. Direct collision. If Pluto were to strike Neptune head-on, it would be almost entirely absorbed by Neptune's dense atmosphere. The impact would generate immense heat, potentially triggering atmospheric disturbances visible across the solar system. However, Neptune's vast size means it would remain structurally intact. A grazing collision. A more likely scenario is a grazing encounter, where Pluto might be torn apart by Neptune's gravitational forces before full impact. This could create a temporary ring system around Neptune, similar to those seen around Saturn and Uranus. Ejection from the solar system. If the gravitational interactions leading up to the collision were significant enough, Pluto might not collide at all, but instead be slingshot out of the solar system, becoming a rogue planet drifting in interstellar space.